Assalamu alaikum. This is lecture 5 on digital control system. We are discussing chapter 2, the Z transform. So the Z transform, as we already said, we are spending a bit of time with this particular topic because of the fact that it enables us the ease of analysis of the digital domain or discrete domain. So today we are going to discuss the inverse Z transform, even though we are supposed to cover a few more properties, but actually we're going to cover those along with the corresponding theory that we have to cover. So let's start the topic today, the inverse Z transform. Okay, so the notation first has been given as Z inverse. This is the notation. And if you have a signal in the Z domain, XZ, and if we apply the Z inverse to that one, and then it should give us X, K, or X, KT. So the value at different time instant, we have to be careful that we are never going to get the time, continuous time signal XKT. So this is what we are not going to get. Rather, time samples are something that we are going to get. So this is one thing we have to be careful. And for finding the values in between the samples, actually we have to introduce zero order hold or first order hold. So some hold circuit will be required or mechanism to actually make it a continuous time signal. We should say piecewise continuous time signal rather than your actual continuous time signal. Okay, so one thing that is important to recall that we only get the information in samples, and information, we don't have any information between the samples. What does it mean? So after conversion, if you have, this is one signal, this is another signal, this is another signal. So maybe the zero, then again increasing, something like this. So in between these two pulses, what is happening? It is not known. This is first thing. Secondly, for the same, for different time, actually it can give you same sample signal. Like if you have a sinusoidal signal, something like this. Okay, and you have another signal, something like this. And your sampling period is something like this, then they will give you same value irrespective of this is your T, this is your twice T, then you have 3T. So after having the inverse Z transformation, we're just getting these values. So these values are same for both the signals. So it's actually difficult to predict what is happening in between the pulses. So you have to be careful while we're actually the design in the discrete domain. Okay, we'll look into this in some later class while we'll be discussing in detail with those whole circuitries and how to find out or reconstruct the original signal similar to the original time domain signal. So that will be also discussed in some future class. But today we like to start with the inverse Z transform. That means today at least we have to happy with xk or xkt. Okay, so let's try to do that. So now for inverse Z transformation, definitely the table 2.1 and table 2.2, basically the Z transform of the fundamental signals as well as the Z transform property will actually help us to find out the inverse Z transformation. So the methods that we are going to see today are methods that we have. 4 of them is mentioned in this book, but in general, in other books, I have seen only 2. So the first one that is common in all books are direct division. Then we have computational method. Then you have partial fraction expansion. And the fourth one is inverse integral method. Inversion integral method. So this one has two segment. One is mathematical using the programming language like Matlab, also Python nowadays. And then secondly, this one has some difference equation approach. Okay, so, and actually in real life, if you really go into designing in digital domain, you actually have to rely on the computational method nowadays because the computer are powerful enough to do those calculations. So the thing that is more common I have found in the books are more common are these red ones, this one and this one, only to do it by hand or pen on paper. In some books, I also have noticed this one with a different name. The name is contour integral method. Okay, so we'll see most of them except the programming part. If I have time in some future classes, I also have those Matlab or Python one. I will try to show them, show those to you. So today, start with the first method. Actually, before going to these methods, one thing we should clear. So poles and zeros in the Z plane, how actually we present them. So poles and zeros in Z plane. So there is two ways we in general represent them in terms of the powers of Z or in terms of power to the minus Z. So there is two ways to represent them. So X Z can be B0 Z to the power M plus B1 Z to the power M minus 1 plus goes on up to Bm divided by Z to the power N plus a1 z to the power n minus 1 plus goes up to an. So in general, the numerator is having more, the denominator has more terms than the numerator. So we assume that the value of n is greater or equal to n. Okay, so based on that, you can call them proper or strictly proper function. Okay, so this is one way, or the same thing can also be represented in this way, exact in terms of poles and the zeros. Z minus Z1, Z minus Z2 goes up to Z minus Zn. And these are zeros, and then we have poles, Z minus P1, Z minus P2. As you can see, these are actually similar to the way we represent in our Laplace domain. Okay, up to Pn. So, and also you may have the coefficient B0 or some constant values. So here, actually, the PIs are poles, and ZIs are zeros. Okay. So now you can represent them, as I said, in terms of to the power of Z, or in terms of to the power of Z inverse. So the same one can be actually also, you can write in this way, that xz equal to, since we assume that the n is greater than n, so numerator and the denominator both will be actually divided by to the power n to find out the solution. Okay, so now let us say we'll have something like this: b0 z to the power minus n minus m plus b1 z to the power minus n minus m plus 1. Eventually it will go up to bm z to the power minus n. Similarly, if you divide the denominator with z to the power m, then we'll have something like this: a1 z inverse plus a2 z to the power minus 2, and goes up to am z to the power minus n. Okay, so these are the two ways. Now, which one is convenient? In general, we always prefer the power. This one is more convenient, and this also has some explanation for that one. So this one is more convenient than we present in this one, but at times we may have to use this one as well. Okay, so especially the direct division one. So now, why we say that this one has some benefits, or for engineers, those who just started in the discrete domain, why digital domain? Why? Because if you have, say, a function xz equal to z square plus 0.5z divided by z square plus 3z plus 2. So we can easily say that if we take z common, then z plus 2, z plus 0.5 will be there at the top, and the denominator, you can also write z plus 1, z plus 2. So you can see that poles are definitely P1 and 2 are minus 1 and minus 2. No question about that. And the zeros are actually Z1 and 2, and that is 0 and minus 0.5. Okay, so these are the poles and the zeros of xz. Now, if you take it into the Z inverse, so basically the denominator and the numerator is divided by z square, and then what we are going to get is 1 plus 0.5 z to the power minus 1 in the numerator, and the denominator will have 1 minus 1 plus 3 z inverse plus 2 z to the power minus 2. So what you can see is that in the new denominator, we can easily find out the similar solution 1 plus z inverse and 1 plus 2 z inverse. So we can easily find those, but in the numerator, what we can see is we don't find that another zero. The zero at minus 0.5, it's available. Poles, there is no problem, right? As you can see, P12 is still same at minus 1 and minus 2. But one of the zero is difficult to identify. So this is one of the difficulties for the beginners to figure out how to find out the other zero. So that is why we prefer this method over this one in terms of pole and zero whenever you're trying to calculate. But with time and practice, it may become easier for you. Okay, so this is one thing. And now, since we know that it's always better to cross-check whether you have calculated the number of the pole zeros properly or not. Now we go into the first method. We have to cover 4 methods, so it will take time. So let's start with the first one, direct division. And also in some literature, you'll find those as long division. Okay, so bottom line is very, very simple. There is 2 simple steps. Expand the xz as a series. Okay, so your first 2 step, expand xz as a series to obtain this xz equal to x0 plus xt z to the minus 1 plus x twice t z to the power minus 2 goes on up to xkt z to the power minus k. So we expanded, and as you can see, these are actually the coefficients of your xt or xkt or xk. Okay, so then once you do that, right then, and then finally, step 2 is just writing the inverse transform as those coefficients. Okay, so sequence something like this: x0, x t, x twice t, xk, and goes on as long as we can go. Okay, so it can also be number sequence. So you can just, instead of t, you can just replace it by number. So x0, x1, x2, then xk, as long as you can do actually. So this is direct division. So let us start with one example. I think this is example of 2.10 of Ogata book. It is asking us to find xk for k equal to 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Only 5 values they're asking to find out with the direct division. And the xz is given. Xz is 10z plus 5 divided by z minus 1, z minus 0.2. Now just multiply and then 10z plus 5 and you have z square minus 1.2z, then you have plus 0.2z to the power minus 2. Okay, so sorry, z 0.2z only, 0.2 only rather. So now next, as you have understood, what we have to do is we have to take it to the other form, negative power of z. So divide both by your higher power, that is z square. So z square, that will give us 10 z to the power minus 1 plus 5 z to the power minus 2. And in the denominator here, 1 minus 1.2 z inverse plus 0.2 z to the power minus 2. Now we are ready for the direct division. The processing is done. So whatever the exact is provided, we have to represent that thing in terms of two polynomials with z to the power negative z with negative powers. And now we have to divide 10, basically 10 z to the power minus 1 plus 5 z to the power minus 2. That has to be divided with this value 1 minus 1.2 z to the power minus 1 plus 0.2 z to the power minus 2. And the first value, since the value is 1, the first one is always it is advantage. So we just give this same value 10 z to the power minus 1. So it will give you 10 z to the power minus 1 minus 12 z to the power minus 2. Then you have 2 z to the power minus 3. Just be a bit careful with the signs. Now it will be 17 z to the power minus 2 because it's changing the, I think you already know, just be careful with the signs, minus 2 z to the power minus 3. So the first parameter again is plus, so plus 17 z to the power minus 2. So 17 z to the power minus 2, then minus 17 to 1.2 will give you 20.4 z to the power minus 3, then plus 70.2, basically double 0.3, so 3.4 z to the power minus 4. So now we have 18.4 z to the power minus 3 minus 3.4 z to the power minus 4. So the next one has to be 18.4 z to the power minus 3. So 18.4 z to the power minus 3 minus 22.08. Okay, z to the power minus 4. And then you have plus 3.68 plus 3.68 z to the power minus 5. Okay, so next one you have 18.68 z to the power minus 4 minus 3.68 z to the power minus 5. So the next value we have to give is 18.68 z to the power minus 4. 18.68 z to the power minus 4 minus 22.46 z to the power minus 5 plus 3.736 z to the power minus 6. So since we have to find out up to z to the power minus 4, we can stop our calculation here. We can say that xz is even expressed in this way. So the first parameter is not available, x0 is not there. So 10 z to the power minus 1 plus 17 z to the power minus 2 plus 18.4 z to the power minus 3 plus 18.68 z to the power minus 4. So it will continue like that if you want. So you can easily write that our first parameter, you can write in terms of, in this way, x0 equal to 0, x1 equal to 10, x2 equal to 17, x3 equal to 18.4, x4 equal to 18.68. So this is one way to present it, or in terms of a sequence, xk equal to, you can also write in this way, 0, 10, 17, 18.4, 18.68, and goes on. Okay, so this is two different ways to represent the same thing. So now long division, I think you already have recognized the problem of the long division. The problem is basically, it is only applicable if you need only for several parameters of the sequence, because otherwise it will go infinitely. So it's very difficult to find out. And also a closed form is not possible out of this one. So only few first parameters of the sequence is what you need. Then you can go for the direct division method, and it will not give you any closed expression unless otherwise we can actually go for some special cases. We may also have some closed form, but it's highly unlikely. So one experiment from the other book, you can, I think, do it by yourself. Is xz is given. So you just find out the corresponding z transform using this long division or direct division. Okay, so maybe say for up to x02 up to x5, something like this. So figure out and try to solve it. Okay, so we don't want to spend too much time on this one. This is relatively simple. There is another example. I think you will be able to do that one as well. This is already worked out example of your Ogata book. So you better just have a look at that one. So xz is given as 1 by z plus 1. Okay, so just take it into the inverse z domain. So z inverse 1 minus z inverse. Now we just divide z inverse by 1 by z inverse, and then you will find out the corresponding values. Okay. So it is also left for you to do. Now go to the next method, that is computational method. So as I said, there is two methods in between, and one is the Matlab or programming, any programming language you can use to figure it out. And also you can plot if you want. So one of the Matlab code is given to you. I personally do not prefer the Matlab because of the fact that even though it is very rich for the simulation, this kind of simulation, because I don't prefer, because most of us don't have the licensed version. So from the ethical point of view, using a pirated software is something that we should not do, unless otherwise we are actually forced And recently I have noticed that we have plenty of alternatives for each and every software, like starting from Microsoft Office, even Windows. Linux is actually far, far better than Windows. Recently, I started using the Linux as well. So there is an option. So once there is an option and still you are preferring to use a pirated software, actually it is something that is, the problem is something that is from our side. So we just have to explore a bit, and inshallah you can have. So if I get time with this codes, then I'll try to show you some codes in Python, inshallah. Even though I am new in the Python, but still we can have some useful libraries, packages dedicated for our control system. Okay, so without taking a long discussion, let's go to the second method. So that is your difference equation approach. Difference equation approach. Okay, so if any particular function is given, say 0.467. Okay, so z to the power minus 1 minus 0.3393, z to the power minus 2. And then you have in the denominator 1 minus 1.5327 z to the power minus 1 plus 0.6607 z to the power minus 2. So difference equation method is useful with actually the other form, that is z positive powers of z. So that is why we are going to multiply this 2 with the highest power of the denominator of the, or the numerator, which is basically z square. So if you multiply z square, then all the parameter will be going to the positive powers of z. Now we can say that this is actually equal to your output by input xz. Okay, so for simplicity, actually as the input we are using the delta function, Kronecker delta function, or actually the impulse, unit impulse as the input. So xk equal to 1 for k equal to 0, and xk equal to 0 everywhere else for k not equal to 0. Sometimes with the limits, I may have made some mistake in the previous lecture. So you just refer to the book and try to correct yourself regarding those. Okay, so what we have here is now why we are taking this one as a input, the unit impulse, or sometimes it is also known as Kronecker delta function, because we know there's a z transformation of this one is xz is basically 1. Okay, so if our input is only 1, then we can easily find out what will be our output. So output y z will be simply then our g of z. So for that advantage, we have taken the Kronecker delta function or unit impulse as a input. So now we have output, input. Now we have our transfer function. Now we can actually just multiply and have the values 0.4673 z minus 0.33 93 divided by z square minus 1.5327z plus 0.6607. Now just cross multiply with those two. And sometimes the calculation of this bit of this course is a bit lengthy, but this is how it is. YZ into Z square minus 1.5327Z 0.6607 equal to 0.4673Z minus 0.3393. So exactly. Now, if you write it in the difference equation form, as you can see that we can say that y z into z square is actually time advance. Okay, so we can say something like this: y k plus 2 advanced by 2, then minus 1.532 y k plus 1 plus 0.6607 yk equal to 0.4673 x k plus 1 and minus 0.3393 x k. So this is our difference equation. Now we know one thing is that x0 is 1, and in rest of the cases x is 0. So using that idea, as well as we know that we're dealing with a causal sequence, so basically y k will also be 0 if k is lesser than 0. Okay, and also xk, x0 is 1, and elsewhere x is whatever the values of k is equal to 0. Okay, so this is the scenario. So based on this one, we can actually take different conditions of k. So say first of all k equal to minus 2. So if k equal to minus 2, so first parameter here will be y0, then 1.532 y minus 2 plus 1, so y minus 1. And then we have 0.6607 y minus 2 equal to 0.4673 x minus 1 and minus 0.3393 x minus 2. So as you can see, x except x equal to 0, everywhere else it is 0, so these are zeros. And this is also 0 because of the causal sequence. This is also 0. So we can easily find that y is 0 equal to 0. So this is the first initial value of y. And secondly, if you take k equal to minus 1, then what we have is y. This is y minus y1, because 2 minus 1 is 1. So y1 minus 1.532 y0 plus you have 0.6607 y minus 1 equal to 0.4673. This is your x0 and minus 0.3393 x minus 1. So x minus 1 is 0. This one has magnitude 1. And this one is 0 because of the causal sequence. This one we just derived to be 0. So we can say that y1 will be 0.4673. Now, next thing that you want to figure out is what is the y1. So for finding y2, you have to take x equal to 0, then y, what we'll have is y0 minus 1.5327 y1 plus 0.6607 y0 equal to 0.4673 x1 minus 0.3393 x0. So x1 is 0, y0 we calculated to be 0, and y1 you can replace the value of 0.4673. So actually, sorry, this will have 2 here. So now y2, after a bit of calculation, basically you take this parameter to the other side and you subtract this value. So it will give you 0.3769. Now you have actually, we should go for, now the main calculation is just started from here because we have to have a sequence from k equal to 0, 1, 2, 3 in this way. So we just done one calculation and I have figured out what is the value. Correspondingly, you can take the value of k equal to 1, 2, 3, and that will give you y3, y4, y5, and goes on. Okay, so this is again a math involved thing. So you have to do it based on the requirement of the problem that has been given. Actually, you can find out that many number of steps to solve this one. Okay, so the next method that is actually partial fraction expansion. So this is your difference equation approach, how to figure it out. Next one is partial fraction expansion. It is most common in most of the book. Okay, so before going to the partial fraction expansion, just one of the useful things to do is reviewing a shifting method. So sometimes in the partial fraction, we use the shifting theorem a bit. So that is why say that we have xz, any functions. So this is your review of shifting theorem. Okay, so xz is given as z to the power minus 1, 1 minus a z inverse. So as we know that we cannot put it into a solution because of the into any format of your common functions z transformation. But what we can do, we can take the z to the other side. We can do is z xz, and we can assume that rest of the thing as yz, and yz we can say the 1 divided by 1 minus a z inverse. We know that this is actually the z inverse of ak is giving us as 1 minus 1 by a z to the power minus 1. So we can say that easily. Now we can take it to the time domain and we can say that it is equal to your ak. So since we have this one, now we can say that xz equal to z inverse yz. So we already figured out what is yz, z transform of the yz. Now it will just give a delay of by 1 time sample. Okay, so or time sequence. So it should give us something like this, a k minus 1. And also, since it is shifted by 1, now instead of starting the counting from k equal to 0, it will be shifted by 1. So k equal to 1, 2, 3. So this should be our sequence now. Okay, so this is a shifting theorem. Why we're doing that? Because at times we are going to see that expanding, instead of expanding xz, because of one of the z in the other side is creating some trouble for your partial fraction expansion. So what you can easily do is, instead of expanding xz, we can easily expand x z by z, or z inverse xz. So you can also do that. So maybe time delay or time advance, that advantage can be taken. So this is why at times the shifted version of, instead of taking the whole the actual function, the shifted version is actually converted, and then finally you just adjust that delay. So this is the review of your shifting theorem, and in the partial fraction, you already know from your classical control theorem, you will have a function in terms of that parameter, which just we have whatever we can previously, z to the power m plus b1 z to the power m minus 1 plus goes on up to bm minus 1 z plus bm divided by z to the power n plus a1 z to the power n minus 1 plus goes on up to an minus 1 z, finally an. So if you expand it in the partial fraction, say, then we'll have something like this. We have to write we can keep the numerator as it is. We just have to write the denominator as a partial fraction, z minus p1, z minus p2, and then it goes up to z minus pm. Now, we can also, for our own benefit, we can actually expand instead of, if you have some z involved here, so you can take the z to the other side, and then you can just expand the rest of the thing in terms of a1 z minus p1 plus a2 z minus p2, and it continues up to an z minus pm. And what is ai? For simple pole, for simple pole, that means at a particular location you have only one pole. AI is calculated as z minus zp, the whole function, that is xz by z that we have, that will be multiplied with that pole, and then you have to set z equal to pi for any arbitrary value of I. But say that in case if you have multiple poles, xz by z has multiple poles or involves multiple poles. Poles, in that case, we have to write equation something like this, and say at z equal to p1, we have two poles, double poles. So xz has z by z can be expanded in this way, c1 by z minus p1 whole square plus c2 by z minus p1. So c1 can be calculated as before. We don't have to bother too much about c1. C1 is simply multiplying z minus p1 square with that function xz by z with setting z equal to p1. So, but for c2, you actually have to differentiate with respect to z, the multiplication, whole multiplication, z minus p1 square xz by z. Okay, and then you have to set it equal to p1. Now, this is for 2, but if you have n number I, say j number of things, so then you will have d by d z. As you can see, there is here one, whatever the coefficient number, you have one less derivative, so you can write it j minus 1. Then you have to write j minus p1. Okay. Actually, it will be better to write actually in terms of Q. So it's up to you. So also you have J number of poles, then Z by Z. Then you have to set Z equal to P J. Okay, so we are just saying that the actually more authentic will be say Q number of Q is the multiplicity. Then it should be writing here Q minus 1 and also Q here because you have to write PJ here. Okay, so this is the way to figure out the partial fraction expansion. So let us look at two examples related to this one. Example 2.14. 2.14 xz is given equal to 1 minus e to the power minus 80 into z divided by z minus 1 and z minus e to the power minus 80. Okay, so we can easily we take z by z equal to, we can easily identify how many poles we have. You can see that we have two poles, one at z equal to minus z equal to, we have two poles at z equal to 1 and z equal to e to the power minus 80. So let us apply the partial fraction. So we have to expand x z by z as say k1 by z minus 1 plus k2 by z minus e to the power minus 80. Okay, so k1, because since both of them are simple pole, there is no multiplicity. So you can write that whatever z, we have to multiply z minus 1 with the whole function, that is 1 minus e to the power minus 80 divided by z minus 1 into z minus e to the power minus 80. And after multiplication, you have to set basically z equal to 1. So as you can say, this one and this one is getting cancelled. If you set z equal to 1, then each they will be cancelling each other. One, they're same thing. So what will be left is 1. Similarly, if you want to calculate the k2, the k2 is z minus e to the minus a2 multiplied with the whole function, that is 1 minus e to the minus 80. Then z minus 1, z minus e to the power minus 80. So now this one and this one is cancelling each other, set z equal to e to the power 80. So now if you set it equal to 80, then what we'll have is 1 minus e to the power minus 80 divided by minus 1 minus e to the power minus 80. So this one is going to be cancelled, so minus 1. So if you put those two values, what we're going to get is xz by z is equal to 1 by z minus 1 minus 1 by z minus e to the power minus 80. Okay, so now finally we can take the z to the other side. Z by z minus 1 minus z by z minus e to the power minus 80. So we can divide the numerator and the denominator by z. So what we have is z inverse, 1 minus z inverse. Okay. And then we have similarly, sorry, we divide by z and okay, so this one will be not there. Rather the simple one will be there, 1 by z inverse. Okay, so and then the other side it will be 1 by 1 minus e to the minus 80 z inverse. Okay, so now what you can see is if we z inverse of this 1 by 1 minus z inverse is basically nothing but it is in terms of 1 or 1 kt, so whatever you like. And similarly, z to the power z inverse 1 by 1 minus e to the power minus 80, z inverse is actually inverse transformation of e to the power minus a kt. Okay, so we have both of them now. So if we can just put it together, then we'll have our xkt or xk. And they have idea in terms of xk, but you can write also in terms of say 1 minus e to the power minus a k. Okay. So this is our simple partial fraction example. There is another complicated one if you want, and you can also go about that one, and that is actually okay. So now, since we are actually not finding the time domain signal, so this is where you have to be careful. So we are not getting the continuous time signal, rather it is a sampled signal. Okay, so now go for the next example, that is example 2.15, another partial fraction example. And it says that you have a function something like this, xz equal to z square plus z plus 2 divided by z minus 1. Then you have z square minus z plus 1. Okay, so in this particular case, so just like in the Laplace domain, what we have done is we have to make it separated. So k1 by z minus 1, so this is 1. And in the other one, since you have square terms, we can write something like this, z square minus z plus 1. Then you can say that k2 z plus k3. Okay, finding the k1 is not that complicated, same as before. And that will give you just z square minus z plus 2 by z square minus z plus 1. And then you set z equal to 1. And as you can see, it will give us the value, basically 4 by 1. So it will give us the magnitude 4. Okay, so 4 by 1, 4. Now, sorry, one thing that is why I was getting confused with how the 4 is coming with actually this plus sign here. Yeah, no, it's 4. Now, for finding the K3 and K4, so the whole equation divided by the whole equation is just multiplied with the numerator, denominator of the equation, the complete equation. So it will give you z square plus z plus 2 equal to K1 z square minus z plus 1 plus K2 z plus K3 z minus 1. Now simplify a bit, z square plus z plus 2 equal to, I'm just skipping one line. So k1 plus k2 z square minus k1 minus k3 plus 1z plus k1 minus k3. Okay, so now if you equate the coefficients in the both side, then we can easily see that k1 minus k3 has to be equal to 2. And we already know k1. So K3 will be simply 4 minus 2, that is 2. And then you have K1 plus K2 will be 1. And we know what is the value of K2. So we can easily find out that K2 will be 1 minus 4. That is actually minus 3. So now what we can write from here as xz equal to 4yz minus 1 plus minus 3z plus 2. Then you have z square minus z plus 1. Okay, so this is a partial fraction. Now there is different way to approach about this one. But there is no question with the first one. So first one is easier to deal with. So first one will be simply the value of 1. Okay, so what about the second one? Second one can be approached in different ways. So in the book, there is 2 methods. So bottom line, partial fraction is done. Now how you approach with finding the similarity with the 4 existing formulas, based on that you can have different approach. So say we just have something like this. We take it first to the z to the power negative values. So basically what we have 4 z to the power minus 1, 1 minus z inverse. Then I was in the other side, what do you have 4? Then minus 3 z inverse plus 2 z to the power minus 2. 1 minus z inverse plus z to the power minus 2. Okay, so now, as I said, the first one is relatively easier. Basically, what you can say is that for z inverse, then this is your 1 minus 1 by z inverse. 1 minus 1 by z inverse is nothing but 1. So we can easily solve that one. Okay, so and a delayed version of 1, basically because of that z inverse. Now about the second one. Now about the second one, how can we approach the second one? There is 2 ways. The first method I'm leaving with you. You look export the book. The second method, what you can do is we can write in this way, minus 3. Then you have z inverse, 1 minus z inverse plus z to the power minus 2 plus 2 into z inverse. So you're just making it a delay. Then z inverse 1 minus z inverse plus z to the power minus 2. Okay, so let us look at the z inverse of z inverse 1 minus z inverse. That is basically 1, magnitude 1 and 0. And for what this is 1. Now since there is a delay, we cannot start from k equal to 0, so it will be k equal to 1, 2, 3. So same thing, instead of delay, we're just starting from the next parameter, and it is k equal to less than or equal to 0. Okay, so the first parameter is done. Now second parameter, and also since our result is 1 and we have a coefficient 4, so to multiply with that, so the result will be 4. And the second and the third actually have a common parameter. So we can just take that common parameter and take the z inverse of that one. That is z inverse 1 minus z inverse plus z to the power minus 2. Now we have to compare this with z inverse. The closest thing that we find is basically with something like this, e to the power minus a k t Z inverse sine omega t divided by 1 minus e to the power minus 2 to the power minus akt. Okay, sorry, actually it was t cos omega t plus e to the power minus 2at z to the power minus 2. So one thing is missing is z inverse here. So this is actually that will give us e to the power a kt minus akt with sine omega t. Sine omega t. So this is the closest thing we have. And as you can see here, we okay. So in the here you have 2 e to the power at and z inverse. Z inverse is already there. 2 is not present, so somehow we have to bring a 2. We have to bring a 2, and likewise we have to divide that 2 as well. And so that half will be actually equal to cos omega t. So cos omega t will be half, and that will give us omega t as pi by 3. Okay, so that omega 3 we can replace it in the numerator as well. So sine pi by 3 is basically root 3 by 2. So we have to somehow bring root 3 by 2 here. And now we have to divide it by 2 by root 3. So to remove that one. And now what is missing is e to the power 80. So e to the power 80 is not there. Okay, so what we have to do is we have to introduce that thing. Okay, so e to the power 80, we can just assume that e to the power 80 to be 1. So we're just assuming that e to the power minus 80 equal to 1. Similarly, e to the power minus twice 80, 80 will be also 1. So we can easily say that we have 1 here. We also have 1 here. We also have 1 in the top. So what we can do is from here is definitely e to the power 1. What we have here is e to the power minus 80 to the power. We have k as well. So we have, since we have used that e to the power 80 is equal to 1, so we can say that 1k is our solution. And here you have sine. Okay, so k actually missing. There was a k. Okay, so omega kt was there by in the formula. So what is our omega t? Omega t is pi by 3. So we can say that this is the formula of actually sine k pi by 3. Okay, so this is the first one, this one. And with that one, you'll have those additional thing will be also going there. And similarly, for the second one, we have a delayed version. So for the second one, we can easily say that whatever we have with the delay of z inverse is basically 1 k minus 1 sine k minus 1 pi by 3. Okay, so if we put all these together with all the coefficients as well, finally, what we are going to get is the solution of this one will be x k equal to 4 minus 2 root 3 sine k pi 3 plus 4 by root 3 sine k minus 1 pi by 3. Okay, so k equal to 1, 2, 3 because of the delay. Okay, so and k is rest of everywhere else, it is basically 0. So this is your partial fraction expansion of a slightly complicated one. So I left it you with the first method. Actually, two different, the solution seems different, but eventually they will produce the same result eventually. Okay, it is almost more than 1 hour. So it is more than 1 hour. So let's stop here, inshallah, and let's discuss the last method, that is contour integral or your inversion integral method, as well as solution of your difference equation using the Z transform. Those two topic of the chapter 2 in the next class, inshallah.